Hello everyone, I am Shubham Jayashree Sridhar Pawar. Welcome back to my channel. So we have completed part 1 and part 2 of ETABS tutorial series which we have started, and we have completed complete modeling of the structure in part 1, and in which we have seen some important clauses of IS 456,000 and IS 13920 2016. In part 2 of video, we have completed or fully concentrated or focused on step number 6, that is, we have assigned conditions to the model. The conditions included support conditions, releases to the beam, diaphragms, and we have also checked the model. Now, in this video, we will concentrate to complete all the remaining steps of the tutorial series, that is still analysis of the structure. So we will concentrate first on load calculations, then define the load patterns, assign loads, define load combinations, and we will analyze the structure. And we will also give some important checks and design the structure. So let's start.
Audio Journey.
Okay, so before starting the load calculations, first we have to see that the loads to be considered in the analysis of the structure. So these are the important loads which I have mentioned in the slide, which we use in the analysis of the structure in any software or even manually. So dead load, first we see dead load. So as we know that while analysis of the structure or designing the structure, we calculate the self-weight of the structure, and self-weight is important concept in analysis and design of structural analysis and structural design. So we will define self-weight of the structure. Here dead load specifically means the self-weight of the structure. So in ETABS, self-weight will come under the type dead load while defining. Now superimposed dead load. Superimposed dead load, basically we can say that it is immovable load. Shown in this image is that the load of brick wall which comes on the beam, then this is the load of plaster, then load of flooring or floor finishes. This all the loads are considered under superimposed dead load. Superimposed dead load we will calculate according to IS 875 part 1. Okay, and live load we will calculate, or live load which we can define as the movable or occupants load. So live load is also calculated or will calculate according to IS 875 part 2. Now wind load is important load in the analysis of the structure. So wind load is calculated according to IS 875 part 3. Okay, and earthquake load. So this is one of the most important load, or seismic analysis is the most important analysis in any structural design or analysis. So earthquake load we will calculate according to IS 1893 2016. So IS 1893, I'm saying IS 1893 2016 because our software is compatible to IS 1893 2016 code. And according to Indian standard, the new code for seismic design has released. So the new code is IS 1893 2025. IS 1893 2025 consists of two parts, that is part 1 and part 5. So we will see in later videos about IS 1893 2025. But as our software is compatible to IS 1893 2016, we will define the loads according to the IS 1893 2016. So let's start now. Okay, so before moving to load calculations, we will first move to ETABS. Okay. Okay, so as we have moved to the ETABS software, so first, as I am in base view, first we will check the conditions which we have applied in the last video. So we have applied this, assigned the support conditions, then releases to the beam and diaphragms. So to see the conditions are assigned or not properly, so first I am checking the support condition. So I am selecting one of the joint or supports, and I'm right click on it. So restraint, yes, so as restraints are showing, so our supports are applied. So in last part I have shown that how to apply support. So now to see that the diaphragms and beams, releases to the beams are applied or not, we will move to the plan view, and in plan view I will move to okay, 1 minute, first floor. And in first floor, so now to see our diaphragms are assigned or not, I will check. Again, I'm moving to view option, and in view option I'm moving to set display option, and in set display option here, diaphragm extent. So applied. Okay, so as I can see, that diaphragm is applied. Okay. Okay. Now, sorry. Now I'm moving to object assignments to check the end releases in object assignments, frame assignments, and in frame assignments, end releases. So end releases, apply. So these are the end releases I have applied in the last video. I request you, the students, to please see the part 1 and part 2 of the tutorial series first. Okay. Okay. So now moving to the today's part. So loads we have considered. So the loads, that is dead load, superimposed dead load, and live and wind and earthquake load, which we have considered, we have to first define in ETABS. So in ETABS software, we have to first define the loads. So I'm moving to define, and in define load patterns. Okay. So as you can see that here one load is given and each type is dead. So as dead load is given, so as I have told that dead load here means that sulfate of the structure. So hence the sulfate multiplier here is 1. Now I am adding live load, superimposed dead load, wind load, and earthquake load. Okay. So first I will add superimposed dead load. Superimposed dead load. Type here will be super dead. So your sulfate multiplier will be 0 only. Okay. If I give a sulfate multiplier any value, or if I even give your value as 1, then ETABS will think that in this load ETABS will also add the sulfate of the structure, which I don't want. So please keep this value as 0 only for rest of the loads. Okay. So superimposed dead load is defined. Now I am defining live load. Okay. So live load. 1 minute. Live load. Okay. So type here will be live only. Here again sulfate multiplier will be 0 only. Again now wind load is. Now in wind load, as we know that wind load is assigned or is defined in two directions. In manual calculations also we see that wind loads are in x direction and y direction also. So we have to define wind load in x and y. Okay. So wind load in x, wind load here type will be wind. Autolateral load, here we have to select the IS code which we are using. So Indian, yes, IS 875 2015. Similarly, for WLY, okay, in both direction. Okay, so now as I have defined the wind load in X and wind load in Y, here selecting wind load in X, I am I'm selecting the option modify lateral load. So okay, so here we have two options: exposure from extent of diaphragms and exposure from shell objects. Now, as in the last video, we have assigned the diaphragms. I am selecting the first option, that is exposure from extents of diaphragms. So there is no need to exposure from shell objects. In later parts of the video, if I make a video, I will also make a video on exposure from shell objects for the students or engineer professionals. But for this tutorial series, I am moving with the option exposure from extent of diaphragm. Okay. So here we have to check this all the options. So wind speed, then terrain category, importance factor, risk coefficients, and topography. So to check this, okay, so now I'm going to PPT, and in PPT, yes, wind load calculations. So I have already written all the things required for the ETABS wind load calculations. So here I needed the basic wind speed. So basic wind speed, that is VB, is 39 meter per second. So this speed is according to annexure A, and this is according to the location we have considered in our analysis. So in our analysis, we have considered the location of structure as Nasik, Maharashtra. So okay, so in wind load, we have to consider wind speed according to the Nasik. So I am moving to the IS code. See, we are using IS 875 2015. Okay, so I'm moving to IS code. Yes, so in annexure A, IS 875 2015, I have also mentioned the page number according to the IS code, which is page number 51. Okay, so for Nasik, as you can see here, for Nasik, the basic wind speed is 39 meter per second. Okay, so I am in ETABS, I am giving the value 39. Okay, now terrain category, importance factor, and risk coefficient and topographic factor. Okay, so I have mentioned the values accordingly, but we will see first in IS code how these values are. So as I have mentioned the page number accordingly. So first we will see the terrain category. So a terrain category is 3. I will show you how. So see K3 or K2. So K2 is here I have mentioned terrain category as category 3. Our height of the structure is around 20 meter. Okay. So I will show in IS code. I have mentioned the page number also in table 2. So I'm moving to the page number 8. So these are the categories value and these are the definition. Okay, so for ETABS um, we have to select terrain categories. So as according to IS code, see 4 categories are given in IS code. So let's see first. Okay, so category 1 is for the exposed open terrain area with few or no obstructions. Then category 2 is for few obstructions or shrubs and buildings or structures having height 10 meter. Okay, and category 3 is generally used for terrain with numerous closely spaced obstructions having size of. Okay, so generally category 3 is used for wind load analysis and category 4 is used for too much closely spaced structures of our structural. Okay, so I am using the category 3 in ETABS. I am also using category terrain category as 3 only. Now importance factor. So importance factor, yes, this is the importance factor. IFCR means importance factor according to coastal region. So importance factor I have here selected one. I will show you according to clause 6.3.4. So I'm moving to ICE code and I'm moving to importance factor C. Okay, so these are the importance factor. As we can see, importance factor for cyclonic region clause 6.3.4. So importance factor I have selected here 1 as according to our structure. So you can also select according to the need. So, so importance factor I have selected 1. Then risk coefficient I have also selected 1. This is according to table 1 of ICE code. So moving to IS code again and moving to, okay, so moving to table 1. So here I have considered all general buildings and structures and according to wind speed that is 39. I have selected it as 1 only. Okay, so our risk coefficient is 1. So in ETABS, okay, 1 is given. Now topographic factor, okay, moving to PPT. Topographic factor I have also selected as 1 only. So again moving to page number 8 now. See topographic, this clause. So according to this clause, we generally, I'm not reading all this stuff now. So according to this clause, we generally select topographic factor for if slope, I am not considering slope, I am considering the ground to plane. So topographic factor for me is 1. So in ETABS also the topographic factor will be 1 only. Okay. Now top story and bottom story will also be okay. The bottom story and top story is okay. Now this is also important part. Now windward coefficient CP and leeward coefficient CP, I will take it as it is given in the software. I am not uh, changing it. Okay, these are the general values and these values are according to, I will show in ICE code also. These values are according to this stuff. This is table number 5, external pressure coefficient. Okay, so I will not change these values, but now in wind directions and exposure widths, here I have to modify. Okay, so in this thing, this option is okay, that exposure set width according to diaphragm extent for the program is okay, but here now as my wind is in x direction, So direction angle here will be 0 only, as it is given that 0 and 90 degree. But for me, as only wind direction is in x, I will cancel the 90-degree angle. Okay. Okay. So, only this will be there. So okay. So same changes I have to do in WLY. Okay, so modify lateral load. Wind speed is 39. Terrain category is 3. Terrain category 3. Importance factor is 1. Then risk coefficient is also 1. Topographic factor is 1. So, yes, wind direction exposure width. Here, as WLY. So, my angle will be 90-degree only. Okay, so these changes we have to do while defining the wind load. Now, uh, after wind load, I am defining seismic load or earthquake load. So similarly, as we have defined the wind load, I have to define earthquake load in x and y direction. So earthquake load in x. So earthquake load type will be seismic here, and IS code we are using 1893 2016. So see, the software is not compatible uh, according to IS 1893 2025. So I am using IS 2016 only. 1 minute, something is okay. So earthquake load in x, I am using seismic, and okay, earthquake load in x and seismic, and okay, so add new load, and similarly in y add new load. Now earthquake load in x, similarly as I have done in wind load calculations, wind load analysis, that I have defined lateral load. Here also I have to modify the lateral load according to our needs. So as it is earthquake load in x, so y direction will be untipped. Eccentric ratio will be 0.05 only. Okay, now response reduction factor and seismic zone factor and site type. This is according to IS 1893 2016. Okay, so I'm moving to PPT, and in wind load seismic load calculation. Okay, the seismic load calculation. So as the seismic zone is 3 and the factor is 0.16 according to Annex E, page number 37 of IS 1893 2016. So moving to IS 1893 2016. Okay, so Annexure E, I'm moving. This is Annexure E. In Annexure E, page number 37, see for Nasik, I'm zooming in. Okay, so for Nasik, as you can see, this is the zone factor and the seismic zone. This is seismic zone. So our seismic zone is 3. Okay, so these are the important data. See, this is according to equivalent static method I am showing you first. So these are seismic data. So for seismic data for in earthquake in x direction, I am giving the seismic zone factor as 0.16. Okay, site type I am considering 2 only. Okay, importance factor. Now importance factor is 1. So importance factor is 1 according to page number 19 or table 8 of IS code. So I'm moving to page number 19. See, I mentioned the page number 19, a page number of codes also for better understanding. Factor all other buildings I have considered. So I have choose one as importance factor. You can choose accordingly. Now importance factor is 1. Now this is the main thing, that response reduction factor. So response reduction factor. So response reduction factor according to IS code, table number 9, page number 20 is given. So in next page. Okay, so these are the conditions given for response reduction factor, and we have to choose accordingly. Okay, so response reduction factor, our structure is first moment frame system. Okay, and our building is RC building, means RCC building. Now these two values are given, that RC building with ordinary moment resisting frame and RC building with special moment resisting frame. So to choose the value, I can choose 3 also, but I have chosen 5. The reason is that because, say in the notes, that RC and steel structures in seismic zone 3, 4 and 5 shall be designed to be ductile. Hence, this system is not allowed. So here IS code is talking about that ordinary frame structure is should not be chosen as the option for seismic zone 3, 4 and 5. So our seismic zone is as 3, so I am choosing the B option. So special moment resisting frame. Okay. So these are all the systems given in IS 1893-2016. You can choose according to the building, but as our plan is simple, I am choosing the B, and response reduction factor here is 5. Okay. Here time period I am not I am moving a time period I am giving according to program calculated only. I am keeping it as it is. So these are the changes we have to do. Okay, so response reduction factor is 5. Now for earthquake in y direction, similar changes I have to do. So I'm doing it. So in y, so y direction plus eccentricity, y direction plus eccentricity again, then minus, then response reduction factor is 5, and then 0.16 as per code is the seismic zone factor. Then site type is 2 only, importance factor is 1, and program calculator. Okay. So yes, so finally our loads are defined in ETABS. Now first, as we have defined the loads, first I will show you. Okay, so first we will see the slide. I have made it for seismic load and methods of seismic analysis. So we calculate the seismic load as we have to design the earthquake resistant building. So according to IS code. And these are the methods of seismic analysis. So in methods, there is static analysis and dynamic analysis. In static analysis, there is equivalent static method and pushover analysis. In dynamic analysis, there is response spectrum method and time history method. So I will make a special video on this method also. And we will also see the manual calculations according to equivalent static method and response spectrum method specifically, as these two methods are widely used. Okay. Now, the Indian Standard Codes use is IS 1893-2016, which we are using in this video. And as I have told you before that IS 1893-2025 has also launched. So before there was only one code, that is IS 1893 Part 1, and now there is two codes for earthquake resistant design is IS 1893 Part 1 and Part 5. So Part 5 is specifically for buildings, okay, and Part 1 is general code for practice or earthquake resistant building. Now the reason is that I have just introduced this method in the slide. Okay, in this video we'll concentrate on equivalent static method and response spectrum method. I have defined the parameters of earthquake resistant building or earthquake load, that is we have defined in ETABS, that is EQX and EQY. So this is according to equivalent static method. Okay, and I will also show you that how the response spectrum analysis is done in ETABS. Okay, so first we will do the static analysis and afterwards the dynamic analysis. So okay, so as we have completed the seismic load methods now, and we have also completed the definitions or load patterns, define the load patterns. So now we have to assign the loads, and to assign the loads, first we have to see the load calculations. So I am moving to the load calculations. See, we have defined the load patterns, and in load patterns we have defined wind load and earthquake load according to the diaphragm. So no need to assign the wind load and earthquake load manually, as we have assigned them already through the exposure extent through diaphragm. So no need to assign them manually. Okay, now we have to assign superimposed dead load and live load. See, dead load is self-weight, so ETABS will take it according to the structure model, but we have to assign manually the superimposed dead load and live load. So I'm moving to the PPT now. Okay, so wind load. Okay, yes, superimposed dead load. So in superimposed dead load, as we have seen, that superimposed dead load is load of, let it be wall, then it will be plaster and floor finish. Okay, so I have calculated according to IS code this slide. Okay, so superimposed dead load. First we will see now the superimposed dead load to assign of flooring excluding the terrace floor. See, the reason why I'm excluding the terrace floor here, because in terrace floor thickness of waterproofing and waterproofing is also done on terrace floor, so the superimposed dead load of waterproofing is also considered. Now first we will see the superimposed dead load for all the floors excluding the terrace floor. Okay, so first, okay, so now we'll see the mortar, the ceiling plaster, and the mortar below the flooring. Okay, so according to IS code, IS 875 part 1, table 2, I'm moving to the table 2. Load intensity for 10 thick mortar is 0.21 as given in IS code. So IS 875 part 1, okay, part 1, and we want mortar. So in table 2, in table 2, mortar scale. Okay, so as you can see, mortar grading for 10 nominal size 0.21 kilonewton per meter square of uh, plaster or mortar, we can say. So see, this mortar I am considering it is the nominal value or standard value given in IS code, and for floor, the mortar below flooring I am considering 50 thick mortar. So as per calculation, 0.21 into 5, so 1.05 kilonewton per meter square mortar below flooring we are getting. So the weight for first superimposed dead load of mortar below flooring we have calculated. Then there, as we know that there is a plaster below the slab. Okay, so ceiling plaster I am considering of 10 only, and as given in IS code, say 10 for 0.21 kilonewton per meter square. Now I am considering the clay floor tiles. So clay floor tiles. Yes, for floor finish for clay floor tiles, according to IS 875, for 12.5 thickness to 25.54 it's 0.10 to 0.2. So I have taken it as 0.2 kilonewton per meter square. See, the total load of floor finish on the floor of all the floors excluding the terrace floor comes to 1.5 kilonewton per meter square. This is the superimposed dead load on the floor. Okay. Now for superimposed dead load for terrace floor, as we know that for terrace floor, damp proof or waterproofing is needed. So I am considering the thickness of waterproofing as 120 Then density of waterproofing we know that 22 kilonewton per meter cube. Then load intensity of waterproofing is 0.12 into 22, that is around 3 kilonewton per meter square. And so for terrace floor, superimposed dead load, see this 0.21, this 0.21 is this ceiling plaster. So as we know that below the slab the plaster ceiling plaster will come, so 0.21 terrace floor total load will be 0.21 plus 3 kilonewton per meter square, so it will be 3.21 kilonewton per meter square. Then as the flooring load or flooring superimposed dead load we have finished, then we have to calculate the superimposed dead load which comes through the wall on the beam. Okay, so superimposed wall load, considering I'm considering the wall width is equal to 230 and wall load, as we know as per the manual calculation, that density into width into height of the wall. So density of the wall I'm considering 20 kilonewton per meter cube. So this density is from IS code, so I'm using the brick wall. Yes, okay, so common burnt brick clay bricks where the density is given as 18.85 kilonewton per meter cube. Now I'm considering it as 20 kilonewton per meter cube. See, we can consider the mode value, because in IS code the values are given as characteristic loads, and these characteristic loads are according to the calculation of, as we can say, the standard deviation. There is a lot of procedure. So wall load we will consider the density I am considering 20 kilonewton per meter cube. Then I am considering wall thickness as 0.23 meter, and I am considering the height of wall as 3 meter, as we have seen in the slide that floor to floor height is 3 meter. So, okay, so I have not calculated. So our wall load will be wall load. So, okay, I'm calculating. Wall load is equal to, so 0.23 into 20 into 3. Okay, so around 13.8, that is 14 kilonewton per meter. Unit will be 14 kilonewton per meter. Yes. So wall load is 14 kilonewton per meter. Now, as we have considered all the superimposed dead load as the wall, then plaster, then ceiling plaster, then floor finish. Now I'm moving to the next part, that is live load or characteristic live load. See, live load is to be considered according to IS 875 part 2. Now I'm moving to IS 875 part 2. See, and I'm considering, so I'm moving to IS 875 part 2 first. Okay, so in IS 875 part 2, say IS 875 part 2 1987 is for the imposed load, which means we are considering the live load here. So yes, different types of buildings are given here. For our, it is the residential building, and for residential building, this respective all the uniformly distributed loads are given for all the rooms and kitchens, toilets and bathrooms, balconies, etc. So we can take accordingly. But for our ETABS model, I am considering the maximum of these values. So the maximum of these values are 3 kilonewton per meter square. So yes, so according to IS code, for floors and staircase, okay, so I am considering 3 kilonewton per meter square. And for terrace floor, see, terrace floor I'm considering 2 kilonewton per meter square, because for terrace floor live load there is less occupancy or less live load present on terrace floor. So I'm considering 2 kilonewton per meter square for terrace floor and for headroom also. So this was the superimposed dead load and live load. Now, now I'm, as we have seen the load calculations, I'm moving to the tabs and we have to assign the loads. So before assigning the loads, I want to define the mass source. Okay, so first I will tell what the mass source is. See, after defining the all the loads, we have to define the mass source according to IS 1893-2016. So first I'm adding the new mass source. See, mass source, I mean to say that in ETABS we are telling the software to consider the gravity loads for seismic design analysis. That is, gravity loads I'm considering as a lump mass. Okay, so in mass source I'm giving the name as mass source as IS 1893 2016, and in IS 1893 2016 specifying specified load patterns I'm considering. And here I'm adding, as I have told already, that adding the load pattern there. Oh, I'm adding the load pattern as gravity loads. So considering the gravity loads, first I have add detailed, then I'm adding superimposed dead load, and I have to add here live load. Okay, but for live load, IS 1893 2016 have given one condition. So I'm moving to IS 1893 2016 part 1. Okay, so yes, so in table 10, see here in table 10, IS code has given one condition that the imposed load we consider for seismic design, the live load we consider for seismic design up to, if we have considered live load up to 3 kilonewton per meter square, we have to consider 25% of the imposed load. Okay, so here in ETABS, as while defining the mass source, I am considering 25% of live load. See, this is according to IS 1893-2016 part 1, table number 10. So okay, so we have defined the mass source. So now here in the options, we have to untick this element self mass because we have considered the dead load already. Okay, so I'm clicking on OK. Okay, so here I am selecting default mass source as IS 1893 2016, and I can also delete this mass source. Yes, so okay. So okay, so our mass source and the load patterns are defined. So I am going to now load cases. So in load cases, in earthquake load cases, here, okay, so mass source is IS 1893 2016. Now, after defining all the load patterns and loads and mass source also, we have to assign the loads to the particular floor. So to assign the loads which we have calculated. See, as I have told, we don't have to assign the earthquake loads and wind loads, as we have already defined and assigned the diaphragm. So I'm assigning first superimposed dead load accordingly of floors first. Okay, first we are moving to the superimposed dead load of floors. So moving to ETABS. To assign the superimposed dead load to floors, I am selecting the object type as floor. So I am selecting the floors. I'm moving to object type, then selected all the floors. Okay, so now moving to view and view show selected objects only. Okay, so now only the floors are seen or available. Okay, so now there is one more option we can do here, that similar story option. But for that, first we have to move to edit, and in edit we have to move to edit story option, and here we have to modify show edit story data. Okay, so I am selecting first floor as master story now, and I'm selecting it. All the stories will be similar to first floor. And see that for terrace floor, our superimposed dead load is different as compared to all the floors remaining. So I'm using the similar story option now. Okay, so now I'm here selecting the similar story option, and in similar story I am clicking on all the floors or selecting all the floors. Okay, and after selecting the floors, you can see that the floors of second floor, yes, floor of second floor up to fourth floor has been selected, as we are using the similar story option. I'm also using, see, terrace floor is not selected because I'm not, the terrace floor doesn't come under the similar story. So moving to plan view and first floor. Okay, so now I have to assign the superimposed dead load on the floor, that is 1.5 kilonewton per meter square, the total load which we have calculated. Where I'm moving to assign, here I have to move to shell loads, and in shell loads uniform, here my load pattern name is superimposed dead load, and direction will be gravity only. Load here is 1.5 kilonewton per meter square. See, the option here will be replace existing loads only, as if we click add to existing load, then ETABS will add new superimposed new load to superimposed dead load. Okay, so here the option will be replaced to existing load only, and our load will be 1.5 kilonewton per meter square, and here I am applying. Okay, so as you can see that the superimposed dead load is applied here. Now after assigning the superimposed dead load, as the live load is also same for all the similar storage floor, I am also assigning the live load similarly. Assign the superimpose dead load or superimpose, sorry, to assign the live load. Okay, so to assign the live load, first I have to select the, we have to follow the same steps now. So I'm selecting the all the floors or the floors till the fourth floor. See, similar story option is important here, so similar story option should be selected all the time. Now, as we know that our live load is 3 kilonewton per meter square, so I am here, load pattern name is live load, and for that 3, the value will be 3, direction will be gravity only, and here I'm apply. Okay, so live load is also applied to check till the fourth floor. See, I'm applying till the fourth floor only because the live load is changed for the terrace floor and headroom. So moving to view, set plan view till the fourth floor. Okay, so as we can see, till the fourth floor, the live load and superimposed dead load for the floors are applied. So yes, see, load pattern name live load and load pattern superimposed dead load is applied. So now I'm moving to apply to terrace floor and headroom now. So I'm again selecting the similar master story. Okay, so modify and show. Here, here my master story here will be terrace floor now. and this terrace floor will be similar to, or see, headroom will be similar to the terrace floor. Okay, refreshing the view, refresh. Okay, so moving to view, set plan view. In set plan view, this is fourth floor. I have to move to the terrace floor now. Okay, so in terrace floor, I have to select all the floors, and in the floors, I have to assign. No, already the okay. The live load for terrace floor is now 2 kilonewton per meter square. So I'm assigning the live load as 2 kilonewton per meter square only. Okay. See, this will be assigned to headroom also. 1 minute. No, not assigned. Oh, okay, moving to edit again. Edit story. Similar story option. Something has been mistaken. Okay, but okay, so it may be software problem. So I'm again assigning the load to headroom. That live load. Live load will be 2. Then moving to set plan view again. Terrace floor. Terrace floor. Okay, so here I am mistaken. See this. So dead load, I have assigned the load pattern name as dead load, so which is wrong. So for terrace floor, okay, so first I will delete the existing load from terrace floor. See, there is no manually load applied because ETABS will consider according to the structure the dead load or the self weight. Now I'm again here moving to live load, and again selecting the option, and here replace the existing load should be selected. Okay, so similar story is also selected. Now I'm assigning the superimposed dead load of terrace floor for waterproofing, that is total is 3.21. So I'm considering it as 3.33. So your superimposed dead load will be 3.33 kilonewton per meter square. Okay, so we can take a round figure of 4 or 3.5 also, but I'm considering 3.33. Now moving to headroom. You can see this moving to headroom. Okay, so adding here also 3.33. Okay, so superimposed dead load is also applied. Now going to view and show all objects. Okay, now I have to add superimposed dead load for wall load. So I'm selecting all the beams or the required beams. Now in ground floor, I have to add to the beam. So selecting all the beams of the ground floor, move to select object type and beams, selecting view, show selected objects only. Now it will be easy because okay, so ground floor, um, assign, in assign, here I have to select the frame loads, and in frame loads distributed option. Okay, so now our load is superimposed dead load, and we have to give the uniform load force here. Replace the existing option, and direction should be gravity only. So as we have calculated wall load as 14 kilonewton per meter, I'm giving the value, assigning the value. Okay, so apply. See, as we can see, so as similar story option is given, so I will check in till the fourth floor. No, so the similar story option is till fourth floor. Okay, so yes, for the beams, 14 kilonewton per meter till the fourth floor is applied. Now, now I am moving to the terrace floor. Okay, so terrace floor, no loads are applied till terrace floor. So I'm considering for terrace floor. Okay, so I am also considering for terrace floor the same options, that I am applying 14 kilonewton per meter square only, 14 kilonewton per meter only. In the plan view, first floor, second floor, third floor, fourth floor, terrace floor, and headroom. Okay, so for all the floors, I have applied the same load. Okay, so now my superimposed dead load and live load and has been assigned. And as we have defined through the diaphragm, our mass source and load pattern for earthquake and wind load has also been defined. So now I'm moving to the load combination. Before analysis, we have seen the load cases. Now I am moving to load combinations. See, we can add the default combinations according to software also. But according to IS code, see, these are the combinations different according to the IS 456 2000 and IS 875 2015 part 5. So I am giving all the or adding all the combinations according to this. So 1.5 dead load plus live load. See, these combinations are all according to the IS 456 2000 as I have given. First of all, this combination is for collapse load, and the combinations this one are for the service load. So we have to write all this and linearly add them. So dead load I will be adding, scale factor here will be 1.5. Then superimposed dead load, the scale factor will be 1.5. Then for live load, the scale factor will be 1.5. So similarly we have to add all the combinations. Okay, so one by one we will add them. See, so after defining all the stuff, I have defined the load combinations according to this. See, these are the service load combinations and these are the collapse load combinations according to IS 456 2000. Okay, so I will tell you the table number. So according to IS 456 2000. Okay, so table number 18 gives the this load combinations. So according to IS 456 2000, and this load combinations I have defined according to this PPT or slide and according to IS 456. So see, I have already defined now. So okay, for the scale factor for the minus EQY or minus WLYLS. See, your scale factor only will change the minus sign. Rest all the things will be similar or same. These are the service load combinations. See, why I am focusing on the service load combinations because they are required for the different checks which we will give after the analysis. So first, after defining the combinations, I am clicking on OK. Now see all the load patterns, then load cases, then load combinations, then mass source has already been defined. Then we have already assigned the loads accordingly. And now we are directly moving to analysis. Okay, but before the analysis, we have to move to select all the stories. Then in select, after selecting all, then I have to move to assign. In assign, see we have to mesh all the things. So in meshing, I am in the frames. I am selecting frame auto mesh option. So here I am selecting auto mesh and then apply. Okay, so mesh are applied to the beams. Similarly, I am selecting all and in all again in assign again in frame. Here frame floor meshing option I have to select and I am here selecting program determine. So the mesh we can see them in assignment. Okay, so analysis and mesh include program determine. Okay, so meshing is done in the frame. Now we have to do mesh in the slabs or shell object. So again I'm selecting all. Again in assign I am moving to shell and in shell I am moving to floor automation option. So here I am selecting the default. Okay, so default mesh is assigned in the for the floors. Okay, see there is one option also that in shell there is wall automation option, but as there is no shear wall present in our structure, so I am not using them. I will make the different or separate video on how to analyze the structure in ETABS using the shear wall. So or when where there is shear wall, how to analyze the structure, but and design also. Design is also given through the software. So see the meshing is done now. So after meshing, I'm again going to check model. See here as the unit is in mm, I'm clicking at 10 mm. shell object. See, now as we have done this meshing, we have to check for the mesh also and check all the option and okay. Yes, so our model has been checked, and as our model is has no warnings, we can move to analysis now. So I'm moving to analysis. In analysis option, first we will see the set degree option, active degree of freedom. So okay, this is full 3D, so it's okay. Now in analysis, I'm set to run case, load cases to run. So these options are okay if there is a warning. Yes, in this option, we have to select calculate diaphragm centers of rigidity. See, why we have to select center of rigidity and these are the important concept, as we know that center of mass and center of rigidity should be close to each other. So while selecting this option rigidity, ETABS will calculate the center of rigidity and center of mass. I will show you after the analysis how it will affect the structure. So first we will click on OK here. Now, okay, so now advanced app option. Yeah, it is showing here advanced solver and program determine the number of integral threads. We can also change the number of integral threads also. Okay, so our structure is small, so I am moving the solver option to the standard solver only. And okay, now I'm running the analysis. In the run analysis first, new window. You can also see the details here. Okay, so the analysis has been performed. So we can also start the animation here. Okay, so see, after the analysis has been performed, we have to give certain checks, but first we'll see the shear force. And so for seeing, first I'm going to undeformed shape in display. Here the forces diagram for the different combinations. See, we can see as we are in headroom, moving to the plan view, first floor. Okay, okay, so yeah, if I select for the combo or for the case for live load or for fill the diagram, yes, see the we can see the shear force. Oh, sorry, we can the moments. We can see the moments there. Then moment in three triplet, that is the maximum moment. And for shear force, yes, the shear force we can see now. So the analysis has been performed. Now, after performing the analysis, the important things which we have to check first is to move to the display option. In display option, first we have to check structural output, and in structural output, see, we have to check the base reactions which are given. So before moving to the checks, I have also told that we will also perform the static and dynamic analysis. That is, I will also perform the response spectrum method. So why we should perform dynamic analysis? So in IS 1893-2016, it is clearly mentioned, see, in clause 7.7.1, that the dynamic analysis should be performed if your building is greater than or longer than 15 meter in height and seismic zone is greater than 2. So our seismic zone is seismic zone number 3, and our building height is also around 20 meters, so it is greater than 15 meter. So we will perform the response spectrum analysis. So before performing, here is some slide that response spectrum analysis. It is a dynamic analysis which provides maximum seismic response of a structure by considering multiple natural modes of vibration. So as we can say that in response spectrum analysis, that considering natural modes of vibration, the maximum seismic response is recorded. There are two methods of determining the story shear force. One is square root of some square, and second is complete quadratic combination, that is CQC method. And we will see first in ETABS. Okay, so first, first as we are in the tables, I'm moving to the, say, center of mass and center of rigidity. Center of mass and center of rigidity should be similar only. Now I'm moving to or close to each other. So now I'm moving to model periods and frequencies. In this, I am copying this. So I am copying these values in Excel here. The reason I will tell you first. So okay, so now to perform, so before performing the checks, I will show you how to perform the response spectrum method or response spectrum analysis. Then I am unlocking the model now. Okay, so moving to define and in define, moving to load patterns. Sorry, to move to define and define, I'm moving to response spectrum functions. In functions, response spectrum. So in response spectrum, I'm choosing the function as Indian Standard 2016. Indian Standard 2016. Okay, I'm adding the new function. Function name, I'm adding response spectrum. So function name, I'm selecting the response spectrum. Our seismic zone is seismic zone number 3. So see, zone factor will be okay. So site type is and response reduction factor is also 5. Okay, so remaining things will be same. I'm clicking it. I'm deleting this spectrum. Okay. Okay, so our response spectrum function has been added. Now again in define. See, this may be a little bit confusing, but this is simple. I'm now moving to the load cases. I'm adding the new case. In adding the new case, I am now giving it as response spectrum, name as response spectrum in X. Okay, so now I am adding the load case type as response spectrum. And here, as I have told you that there are two methods of calculating the shear force or story shear, that is square root of sum of square and complete quadratic combination method. So according to IS code and the reason why I have uh, copied this or pasted in Excel is, see, the IS code or the different codes tells that when there is closely spaced modes, for closely spaced modes, the method should be selected as complete quadratic combination method. And in general also the complete quadratic combination method is selected. So and if the modes are not closely spaced, we can select the square root of square method. But for our model combination, I'm selecting CQC method. Directional combination also I'm selecting CQC3. Okay, so I'm here adding the function or adding the load case. Here acceleration as load case is RSX. I am adding it U1. Here it will be U1 only. Default uniform. Now scale factor. See, scale factor is the factor used to scale the model if VB static is greater than VB dynamic. So VB static is greater than VB dynamic. We will check this after the analysis. See, IS code also says the same. This clause. See, IS 7.7.3 says that if the static analysis reactions or results is shear or base reaction is greater than shear reaction is greater than the dynamic analysis or response spectrum reaction, then the scale factor, so the ratio of scale factor is given as it is to we can say to make the values similar to the static analysis. Okay, if the condition is that if static analysis results are greater than the dynamic analysis share values. Okay, but first we have to check if the case is uh, if it happens or not. Okay, so I have uh, defined the load case in X direction. Now I am again adding the new case. Now this case will be in Y direction, and for Y direction I am adding the function or case type as load response spectrum. It will be the CQC. This will be the CQC3. Adding the function, adding the load case type, then U2. We will change the scale factor if it is required. First we will do the analysis. Okay, so after completing the definition for response spectrum analysis, I am moving to analysis command and run analysis again. Okay, so we have completed the analysis part now. So now after completing the analysis, we have to check if the scale factor is needed or not. So I am moving to display, show table. Here we have to check structural output, base reactions, and case type. Here I will select 1 minute, sorry, in case type, in output case, I will select earthquake cases. So earthquake in X direction, earthquake in Y direction, then response spectrum in X, response spectrum in Y. Okay, so now from the values as in the table, it is seen that the value, that is if RSX value is greater than EQX and RSY value is greater than EQY. So as the condition is there that this scale factor is used if the base share or the share of static analysis is greater than dynamic analysis. But in our case, dynamic analysis values are greater than static analysis. So there is no need to use the scale factor. Now, again moving to ETABS now. Now as we have completed the analysis part, I am now moving to the checks part. Okay, so see, we are giving 3 checks according to the respective I scopes. So first check is check for story drift. Then second is check for torsional irregularity. Third check for lateral sway. Okay, so now check for story drift. Check for story drift. First we'll see the check for story drift. This check is according to the clause 7.11.1.1 of IS 1893 2016 part 1. So moving to IS code. Okay, so IS 1893 2016. Okay, yes. So in 7.11.1.1 clause, which is on page number 26 of IS 1893 2016 part 1. So see, this is the clause, that is story drift. So according to the clause, that story drift in any story shall not exceed 0.004 times the story height under the action of design base of shear, with no load factors mentioned in 6.3, that is with partial safety factor of all the loads taken as one. So see, so this clause first will first, what is story drift? So story drift is nothing but relative displacement between flows above and below the story. And according to the clause, that story drift value should not of any story should not exceed 0.004 times the story height. And here the partial safety factor is 1. That means we have to give the check for service load combinations. So I have already made the Excel sheet. Okay, so moving to the Excel sheet now. Yes, so this is the Excel sheet I have made for story drift check, torsional irregularity check, and lateral switch check. So we'll also try to share the Excel sheet with you. So story. So first we will see the row, that is story, then load combination, then direction, and ETABS drift, story drift, allowable drift, and check. Okay. So first we will see the story, then Here the story names will be mentioned, then the load combinations which are the service load combination, then directions which are the x and y directions, then ETABS stripped. Then from ETABS stripped I will also tell how to calculate the story drift, and I've already okay, so here, yes, so I have already assigned the formula for the allowable drift and check. So we will go step by step. So I move to ETABS. In ETABS, for story drift limitation or story drift check, according to IIS clause 7.11, uh, first move to display, then show tables. In show tables, in structural output, so in joint output, sorry, in joint output, move to displacement, and in displacement specifically move to story drift table. So in story drift table, okay. So now output case here we have to select only the service load combinations. So I am selecting service load combinations particularly. Okay, so service load. Yes, so service load combinations are been selected. Here direction I will select as sort by ascending, and after selecting this direction sort by ascending I will copy the table. Okay, so first story. So story, I am mentioning here story. Okay, so this has to be deleted, and the rest of the part will be cut and paste. Okay, then load combinations are the load combinations which are the output case here, and the service load combinations. So yes, so output case has been copied in the load combinations. Then after load combinations I am copying the direction. So again in the tabs, direction column, see I have sort it by ascending, so it will give me direction first x and then after the y directions in a sequence, okay, not randomly. So I have copied the direction. Now the main part is to copy the tabs drift. Yeah, so drift values I am copying in Excel sheet. Okay, okay, now after ETABS drift, we have to calculate the story drift. So see, story drift formula will be, it will be ETABS drift into the story height. So our story height is 3 meter, that is 3000, okay, in mm. So our story drift will be something like this according to the formula. So I am just dragging it down, so it will be applied to all cells, particularly in the table. Now allowable drift formula is the check which we have to give, that is allowable story drift should not exceed, or allowable drift should be 0.004 into total story height. So our total story height is 3000, that is 3 meter and 3000 mm. So the formula I have already added. Okay, so something unmerged first. Okay, so story drift. Okay, so I have not tracked the story drift till down. Okay, so story drift. Yes. Yes, so story drift I have dragged it down now. Then allowable drift I am dragging cell. So first we have to unmerge the cells, and okay, so allowable drift is 12. Now for the check, as it is mentioned that the check we have to give that the allowable drift value or the story drift value should not exceed the allowable drift value. So it which I have mentioned in the formula that this value should not exceed this. So if this value exceeds uh, or the story depth values exceeds 12, then it will give the result as error or fail. Okay, so I am dragging it down now. Okay, so now you can see that are all the values are true. So our check for story drift has passed. Okay, so now I'm saving it first. Okay, so now I'm moving to check number 2, that is check for torsional irregularity. So check for torsional irregularity, that is according to clause number 7.1, table number 5, page number 14 of IS 1893 2016. So moving to IS code. Okay, so page number 14. Yes, so torsional irregularity check says that, see this clause, 1 minute, see this clause. A building is said to be torsionally irregular when the maximum horizontal displacement of any floor in the direction of the lateral force at one end of the floor is more than 1.5 times its minimum horizontal displacement at the far end of the same floor in the direction. So see this figure here says all the things. So the stuff written here is noted in this figure that, see, if delta minimum or if delta max here is greater than 1.5 of delta minimum, then the building is said to be torsionally irregular. So now find the torsionally irregular, or to give the torsionally irregular check. So we are moving to ETABS again, and here, okay, so now here road drift is over now. So here now I'm moving to display again. In display I am show tables. In show tables, joint output again, displacements. Now in displacement, I am selecting this table now, story max over average displacement. Okay, and here I am selecting output case as the earthquake case only. Okay, so sorry. So after selecting the earthquake case only, okay, so now after selecting the output case, here I am selecting sort by ascending. Now, after selecting the sort by ascending, I have also made the Excel sheet for torsional irregularity check, in which story column, then load case column, direction, and maximum displacement and average displacement here means the minimum displacement, and their ratio and the check. So we'll go step by step again in this. So in ETABS, we will copy the respective column and paste here. Okay, so story will be deleted. then load case will be see we have only selected the uh, earthquake load cases. Okay, direction will be X and then simultaneously Y. Okay, so direction copying, software direction, Excel sheet, yes. So direction is copied. Now the maximum displacement value I have to copy. The maximum displacement value is in mm. Okay, so I am copying. Similarly, I have to copy the average displacement value and their ratio also, but okay, we will copy one by one. Okay, the ratio. Okay, so now see, according to the check, if we go according to the check, then the ratio value should be less than 1.5. Okay, so here the reference. Okay, okay, so this. Okay, okay, so now this ratio value should be less than 1.5. If this value is greater than 1.5, a check will be failed. Okay, so I'm dragging this check till the respective values. Okay, so a check for torsional irregularity has passed, so I'm saving it. Okay, now we are moving to the our third and last check of lateral switching. So this is according to IS 456 2000. Okay. Okay. So see, check for lateral sway, clause number 20.5, page number 33 of IS 456 2000. So moving to IS 456 2000. Okay. So if it is okay, so it is not open here. Okay, so I am open now the IS 456 2000, and here according to clause 20.5. Yes, 20.5. See this clause, lateral sway. So in lateral sway, under transient wind load, the lateral sway at the top should not exceed h by 500, where h is the total height of the building. And for seismic loading, reference should be made to IS 1893 to the 1893. Okay. So see, this clause tells us that we have to select the wind load here. Means the load cases we have to check for wind load cases, and h by 500. So h by 500 is h by 500 value. So we have to check for h by 500 value, that our wind load cases lateral sway, that is the maximum displacement only value, should not be more than this value, h by 500 ratio. So we will go to ETABS again now. So first we will move to the Excel sheet which I have made. Okay. Okay, so this is the Excel sheet which I have made for lateral switching. See, I will also try to share the Excel sheet with you. Okay. So now story, then load case, then direction, then maximum displacement, and H by 500. Okay, so here in the same table, because this is the maximum displacement table only, we have to select the output case for wind load only. Okay, so we will select the output case for service wind load combination here. Okay, so wind load combinations. Okay, I have selected earthquake load also. So here I will select only service wind load combinations according to IS 20.5. Okay, apply. And one more thing mentioned in IS code is that under transient wind load, the lateral sway at the top. So at it as it is mentioned, the lateral sway is at top. We have to check it for only store headroom. Okay, so I am only clicking on headroom. See, so these are the stories, and okay, now copying, moving story, then load case load case are only related to wind loads. Then direction here, and the maximum displacement should be copied here. Okay, now here h by 500. So our height of the building, as we know that it is around 20 meter, so 20,000 mm it will be divided by 500. Okay, so our value is 40 mm, and according to the check, our value should not be greater than the h by 500 value. So I'm dragging it, and this also. Okay, so our check for lateral sway has passed. So see, our all the three checks are been passed. So our three checks, that is check for story drift, check for torsional irregularity, and check for lateral sway has been completed. Now we will move to the design part. So for design part, in ETABS, after analysis, I will move to design. In it, I will move to concrete frame design. First, I will check the view reference part. So IS 456 and step by step all. So all the part is okay here. Now again move to design, concrete frame design. Select the group. Here I will select all the groups. Then again move to design. Then select load combinations. So here I will select all the load combinations. Okay. And in design, again concrete frame design. Now I am starting the check, design check. See, so after designing are all the uh, columns and parts have been designed. So as if I click on the one of the column and right click them, so here I will get the reinforcement, and if I go to details, see, we can see the reinforcement here and the report of the reinforcement. So this is how the uh, structure is designed in the ETABS. So see, so we have completed the design of the design analysis and design of the all the ETABS tutorial series. Actually, we have completed ETABS tutorial series now. In this ETABS tutorial series, we have completed follow this. We have completed all the steps till step number 13. Okay, so we have designed the structure also in software. We have not designed it manually. In the next videos, I will try to teach the design using manually. This tutorial series helps the students or the structural engineering professionals. These videos I have made basically for the beginners. So hope it helps them. So thank you for watching, and please like, share and subscribe my channel. Thank you.